Recurrence relations and recursive algorithms, Part 1. Welcome friends, let us consider the following problem. The number of bacteria in a colony doubles every hour. If a colony begins with 5 bacteria, how many will be present in n hours? To solve this problem, let n be the number of bacteria at the end of n hours. Because the number of bacteria doubles every hour, the relationship an is equal to 2an minus 1 holds whenever n is a positive integer. This relationship, together with the initial condition a0 is equal to 5, uniquely determines an for all non-negative integers n. We can find a formula for an from this information. This method, in which a counting problem can be solved by finding a relationship, is called recurrence relation. In this section, we will study a variety of counting problems that can be modeled using recurrence relations. When we define a set recursively, we specify some initial elements in a basis step and provide a rule for constructing new elements from those we already have in the recursive step. A rule of the latter sort, whether or not it is a part of recursive definition, is called a recurrence relation. Such relations can be used in studying and solving counting problems. Definition: a definition such that the object defined occurs in the definition is called a recursive definition. For instance, the Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13, etc. is defined as a sequence whose first two terms are f0 is equal to 0, f1 is equal to 1, and each subsequent term is the sum of two previous ones, that is fn is equal to fn minus 1 plus fn minus 2 for n greater than or equal to 2. Other examples: recursive definition of factorial, that is 0 factorial is equal to 1. N factorial is equal to n into n minus 1 factorial for n greater than or equal to 1. Another example: recursive definition of power. A raised to 0 is equal to 1. A raised to n is equal to a raised to n minus 1 into a for n greater than or equal to 1. In all these examples, we have an initial conditions where the function is explicitly evaluated for one or more values of its argument. A recursive step stating how to compute the function from its previous values. Definition 2. A recurrence relation for the sequence an is an equation that expresses an in terms of one or more of the previous terms of the sequence, namely a0, a1, etc. an minus 1 for all integers n with n greater than n0, where n0 is a non-negative integer. Definition 3. A sequence is called a solution of a recurrence relation if its terms satisfy the recurrence relation. Example: in the recursive definition of the Fibonacci sequence, the recurrence is fn is equal to fn minus 1 plus fn minus 2 with initial conditions f0 is equal to 0, f1 is equal to 1. Another example: check whether the sequence an where an is equal to 3n for every non-negative integer n is a solution of the recurrence relation an is equal to 2 into an minus 1 minus an minus 2 for n is equal to 2, 3, 4, etc. Answer the same question where an is equal to 2 raised to n. Solution: suppose that an is equal to 3n for every non-negative integer n. Then for n greater than 2, we see that 2 into a n minus 1 minus a n minus 2 is equal to 2 into 3 into n minus 1 minus 3 into n minus 2 is equal to 3n and is equal to a n. Therefore, a n where a n is equal to 3n is a solution of the recurrence relation. Suppose that a n is equal to 2 raised to n for every non-negative integer n. Note that a0 is equal to 1, a1 is equal to 2 and a2 is equal to 4. Because 2 into a1 minus a0 is equal to 2 into 2 minus 1 is equal to 3, not equal to a2, we see that an where an is equal to 2 raised to n is not a solution of the recurrence relation. Linear recurrence relations. A wide variety of recurrence relations occurs in models. Some of these recurrence relations can be solved using iteration or some other ad hoc technique. However, one important class of recurrence relations can be explicitly solved in a systematic way. These are recurrence relations that express the terms of a sequence as linear combinations of previous terms. Definition 6. Kth order linear recurrence relation is of the form C0 into an plus C1 into an minus 1 plus C2 into an minus 2 plus etc. plus Ck into an minus k is equal to Bn, where C0 not equal to 0. If Bn is equal to 0, the recurrence relation is called homogeneous. Otherwise, it is called non-homogeneous. The coefficients Ci may depend on n, but here we will assume that they are constant unless otherwise stated. Note: a general form of a linear homogeneous recurrence relation of degree k with constant coefficients is of the form an is equal to C1 into an minus 1 plus C2 into an minus 2 plus etc. plus Ck into an minus k, where Ci are real numbers with the Ck not equal to 0. The recurrence relation in the definition is linear because the right hand side is a sum of previous terms of the sequence, each multiplied by a function of n. The recurrence relation is homogeneous because no terms occur that are not multiples of aj's. The coefficients of the terms of the sequence are all constants rather than functions that depend on n. The degree is k because an is expressed in terms of the previous k terms of the sequence. Example 7. The recurrence relation Pn is equal to 2 into Pn minus 1 is a linear homogeneous recurrence relation of degree 1. The recurrence relation Fn is equal to Fn minus 1 plus Fn minus 2 is a linear homogeneous recurrence relation of degree 2. The recurrence relation An is equal to An minus 5 is a linear homogeneous recurrence relation of degree 5. Example 8. The recurrence relation An is equal to An minus 1 plus An plus 1 square is not linear. The recurrence relation Hn is equal to 2 Hn minus 1 plus 1 is not homogeneous. The recurrence relation Bn is equal to n into Bn minus 1 does not have constant coefficients. Linear homogeneous recurrence relations are studied for two reasons. First, they often occur in modeling of problems. Second, they can systematically solved. Solving linear homogeneous recurrence relation with constant coefficients. The basic approach for solving linear homogeneous recurrence relation is to look for solutions of the form An is equal to r raised to n, where r is a constant. Note that An is equal to r raised to n is a solution of the recurrence An is equal to C1 into n minus 1 plus C2 into n minus 2 plus etc. plus Ck into n minus k if and only if r raised to n is equal to C1 into r raised to n minus 1 plus C2 into r raised to n minus 2 plus etc. plus Ck into r raised to n minus k is equal to 0. When both sides of this equation are divided by r raised to n minus k and the right hand side is subtracted from the left, we obtain the equation r raised to k minus C1 into r raised to k minus 1 minus C2 into r raised to k minus 2 minus etc. minus Ck minus 1 into r minus Ck is equal to 0. Consequently, the sequence An is equal to r raised to n is a solution if and only if r is a solution of this last equation, which is called the characteristic equation of the recurrence relation. The solution of this equation are called the characteristic roots of the recurrence relation. As we will see, these characteristic roots can be used to give an explicit formula for all the solutions of the recurrence relation. Let R1, R2 be two in general complex roots of the above equation. They are called characteristic roots. We distinguish three cases. Theorem 9. Let C1 and C2 be real numbers. Suppose that R square minus C1R minus C2 is equal to 0 has two distinct roots R1 and R2. Then the sequence An is a solution of the recurrence relation An is equal to C1 into An minus 1 plus C2 into An minus 2 if An is equal to alpha 1 into R1 raised to n plus alpha 2 into R2 raised to n for n is equal to 0, 1, 2 etc. where alpha 1 and alpha 2 are constants. Let C1 and C2 be real numbers. Suppose that R square minus C1R minus C2 is equal to 0 has single root R0. Then the sequence An is solution of the recurrence relation An is equal to C1 into An minus 1 plus C2 into An minus 2 if An is equal to alpha 1 into R naught raised to n plus alpha 2 into n into R naught raised to n for n is equal to 0, 1, 2 etc. where alpha 1 and alpha 2 are constants. Proof. We will show that if An is equal to alpha 1 into R1 raised to n plus alpha 2 into R2 raised to n, then the sequence An is a solution of the recurrence relation. Because R1 and R2 are roots of R square minus C1R minus C2 is equal to 0, it follows that R1 square is equal to C1 into R1 plus C2, R2 square is equal to C1 into R2 plus C2. From these equations, we see that C1 into An minus 1 plus C2 into An minus 2 is equal to C1 into alpha 1 into R1 raised to n minus 1 plus alpha 2 into R2 raised to n minus 1 plus C2 into alpha 1 into R1 raised to n minus 2 plus alpha 2 into R2 raised to n minus 2 is equal to alpha 1 into R1 raised to n minus 2 into C1 R1 plus C2 plus alpha 2 into R2 raised to n minus 2 into C1 R2 plus C2, which is equal to alpha 1 into R1 raised to n plus alpha 2 into R2 raised to n and is equal to An. This shows that the sequence An with An is equal to alpha 1 into R1 raised to n plus alpha 2 into R2 raised to n is a solution of the recurrence relation. The second part may be proved in a similar way. Example 10. What is the solution of the recurrence relation An is equal to An minus 1 plus 2 into An minus 2 with A0 is equal to 2 and A1 is equal to 7. Solution. The characteristic equation of the recurrence relation is R square minus R minus 2 is equal to 0. Its roots are R is equal to 2 and R is equal to minus 1. Hence, the sequence An is a solution to the recurrence relation if and only if An is equal to alpha 1 into 2 raised to n plus alpha 2 into minus 1 raised to n for some constants alpha 1 and alpha 2. Next, we will use initial conditions to get the values of alpha 1 and alpha 2. From the initial conditions, it follows that A0 is equal to 2 is equal to alpha 1 plus alpha 2. A1 is equal to 7 is equal to alpha 1 into 2 plus alpha 2 into minus 1. Solving these two equations, we get that alpha 1 is equal to 3 and alpha 2 is equal to minus 1. Hence, the solution to the recurrence relation satisfying the initial conditions is the sequence An is equal to 3 into 2 raised to n minus 1 raised to n. What is the solution of the recurrence relation? An is equal to 6 into An minus 1 minus 9 into An minus 2 with initial conditions A0 is equal to 1 and A1 is equal to 6. Solution. The characteristic equation of the recurrence relation is r square minus 6r plus 9 is equal to 0 and its only root is r is equal to 3. Hence, the solution to this recurrence relation is an is equal to alpha 1 into 3 raised to n plus alpha 2 into n into 3 raised to n for some constants alpha 1 and alpha 2. Using the initial conditions, it follows that a naught is equal to 1 is equal to alpha 1, a1 is equal to 6 is equal to alpha 1 into 3 plus alpha 2 into 3. Solving these two equations shows that alpha 1 is equal to 1 and alpha 2 is equal to 1. Consequently, the solution to this recurrence relation satisfying the initial conditions is an is equal to 3 raised to n plus n into 3 raised to n. We will now state the general result about the solution of linear homogeneous recurrence relations with constant coefficient, where the degree may be greater than 2 under the assumption that the characteristic equation has distinct roots. Theorem 11. Let C1, C2, etc. Ck be real numbers. Suppose that the characteristic equation r raised to k minus C1 into r raised to k minus 1 minus C2 into r raised to k minus 2 minus etc. minus Ck minus 1 into r minus Ck is equal to 0 has k distinct roots r1, r2 etc. rk. Then a sequence an is a solution of the recurrence relation an is equal to C1 into an minus 1 plus C2 into an minus 2 plus etc. plus Ck into an minus k if and only if an is equal to alpha 1 into r1 raised to n plus alpha 2 into r2 raised to n plus etc. plus alpha k into rk raised to n for n is equal to 0, 1, 2 etc. where alpha 1, alpha 2 etc. alpha k are constants. We illustrate the use of theorem with following example. Problem. Find the solution to the recurrence relation an is equal to 6 into an minus 1 minus 11 into an minus 2 plus 6 into an minus 3 with the initial conditions a naught is equal to 2, a1 is equal to 5 and a2 is equal to 15. Solution. The characteristic equation of this recurrence relation is r cube minus 6r square plus 11r minus 6. The characteristic roots are r is equal to 1, r is equal to 2 and r is equal to 3 because r cube minus 6r square plus 11r minus 6 is equal to r minus 1 into r minus 2 into r minus 3. Hence, the solution to this recurrence relation are of the form an is equal to alpha 1 into 1 raised to n plus alpha 2 into 2 raised to n plus alpha 3 into 3 raised to n. To find the constants alpha 1, alpha 2 and alpha 3, use the initial conditions. This gives a naught is equal to 2 is equal to alpha 1 plus alpha 2 plus alpha 3, a1 is equal to 5 is equal to alpha 1 plus 2 into alpha 2 plus 3 into alpha 3, a2 is equal to 15 is equal to alpha 1 plus 4 into alpha 2 plus 9 into alpha 3. When these three simultaneous equations are solved for alpha 1, alpha 2 and alpha 3, we find that alpha 1 is equal to 1, alpha 2 is equal to minus 1 and alpha 3 is equal to 2. Hence, the unique solution to this recurrence relation and the given initial conditions is the sequence an with an is equal to 1 minus 2 raised to n plus 2 into 3 raised to n. Linear non-homogeneous recurrence relations with constant coefficients. We have seen how to solve linear homogeneous recurrence relations with constant coefficients. Next, we will see is there a relatively simple technique for solving a linear but not homogeneous recurrence relation with constant coefficient such as an is equal to 3 into an minus 1 plus 2n. We will see that the answer is yes for certain families of such recurrence relations. A recurrence relation of the form an is equal to C1 into an minus 1 plus C2 into an minus 2 plus etc. plus Ck into an minus k plus Fn, where C1, C2 etc. Ck are real numbers and f of n is a function not identically 0 depending only on n. The recurrence relation an is equal to C1 into an minus 1 plus C2 into an minus 2 plus etc. plus Ck into an minus k is called the associated homogeneous recurrence relation. It plays an important role in the solution of the non-homogeneous recurrence relation. Example, each of the recurrence relations an is equal to an minus 1 plus 2n, an is equal to an minus 1 plus n minus 2 plus n square plus n plus 1, and an is equal to 3an plus n into 3 raised to an is equal to an plus n minus 2 plus n minus 3 plus n factorial is a linear non-homogeneous recurrence relation with constant coefficients. The associate linear homogeneous recurrence relations are an is equal to an minus 1, an is equal to an minus 1 plus an minus 2, an is equal to 3 into an minus 1 and an is equal to an minus 1 plus an minus 2 plus an minus 3 respectively. The key fact about linear non-homogeneous recurrence relations with constant coefficient is that every solution is the sum of a particular solution and a solution of the associated linear homogeneous recurrence relations, as the following theorem shows. Theorem 12. If AP is a particular solution of the non-homogeneous linear recurrence relation with constant coefficients, an is equal to C1 into n minus 1 plus C2 into n minus 2 plus etc. plus Ck into n minus k plus f of n, then every solution is of the form AP plus AH, where AH is a solution of associate homogeneous recurrence relation. An is equal to C1 into n minus 1 plus C2 into n minus 2 plus etc. plus Ck into n minus k. By this theorem, we see that the key to solving non-homogeneous recurrence relations with constant coefficients is finding a particular solution. Then every solution is a sum of this solution and a solution of the associated homogeneous recurrence relation. Although there is no general method for finding such a solution that works for every function f of n, there are techniques that work for certain types of functions f of n, such as polynomials and powers of constants. Theorem 13. Suppose that an satisfy the linear non-homogeneous recurrence relation an is equal to C1 into n minus 1 plus C2 into n minus 2 plus etc. plus Ck into n minus k plus f of n, where C1, C2 etc. Ck are real numbers and f of n is equal to Bt into n raised to t plus Bn minus 1 into n raised to t minus 1 plus etc. plus B1 into n plus B0 into whole s raised to n, where B0, B1 etc. Bt and s are real numbers. When s is not a root of the characteristic equation of the associated linear homogeneous recurrence relation, there is a particular solution of the form Pt into n raised to t plus Pn minus 1 into n raised to t minus 1 plus etc. plus P1 into n plus P0 the whole into s raised to n. When s is a root of this characteristic equation and its multiplicity is m, there is a particular solution of the form n raised to m into Pt into n raised to t plus Pn minus 1 into n raised to t minus 1 plus etc. plus P1 into n plus P0 the whole into s raised to n. Note that in the case when s is a root of the multiplicity m of the characteristic equation of the associated linear homogeneous recurrence relation, the factor n raised to m ensures that the proposed particular solution will not already be a solution of the associate linear homogeneous recurrence. We will illustrate these theorems with following examples. Example 14. Find all solutions of the recurrence relation an is equal to 3 into an minus 1 plus 2n. What is the solution with a1 is equal to 3? Solution. To solve this linear non-homogeneous recurrence relation with constant coefficients, we need to solve its associated linear homogeneous equation and to find a particular solution for the given non-homogeneous equation. The associated linear homogeneous equation is a n is equal to 3 into a n minus 1. Its solutions are a n h is equal to alpha into 3 raised to n, where alpha is a constant. We now find a particular solution. Because f of n is equal to 2n is a polynomial in n of degree 1, by this theorem, particular solution is a linear function in n, say p n is equal to c into n plus d, where c and d are constants. It should satisfy the recurrence relation. Then the equation a n is equal to 3 into a n minus 1 plus 2n becomes c n plus d is equal to 3 into c into n minus 1 plus d plus 2n. Simplifying and combining like terms gives 2 plus 2z into n plus 2d minus 3c is equal to 0. It follows that c into n plus d is a solution if and only if 2 plus 2z is equal to 0 and 2d minus 3z equal to 0. This shows that c n plus d is a solution if and only if c is equal to minus 1 and d is equal to minus 3 by 2. Consequently, a n p is equal to minus n minus 3 by 2 is a particular solution. By theorem, all solutions are of the form a n is equal to a p plus a h is equal to minus n minus 3 by 2 plus alpha into 3 raised to n. To find the solution with a 1 is equal to 3, let n is equal to 1 in the formula we obtain for the general solution. We find that 3 is equal to minus 1 minus 3 by 2 plus 3 into alpha, which implies that alpha is equal to 11 by 6. The solution we seek is a n is equal to minus n minus 3 by 2 plus 11 by 6 into 3 raised to n. Now, try to solve the given questions. 1. A model for the number of lobsters caught per year is based on the assumption that the number of lobsters caught in a year is the average of the number caught in the 2 previous years. Find a recurrence relation for Ln, where Ln is the number of lobsters caught in a year n under the assumption for this model. 2. Solve these recurrence relations together with the initial conditions given. A n is equal to a n minus 1 plus 6 into a n minus 2 for n greater than or equal to 2, a naught is equal to 3, a 1 is equal to 6. 3. Find the solution to a n is equal to 2 into a n minus 1 plus a n minus 2 minus 2 into a n minus 3 for n is equal to 3, 4, 5, etc. with a naught is equal to 3, a 1 is equal to 6 and a 2 is equal to 0. 4. Consider the non-homogeneous linear recurrence relation a n is equal to 3 into a n minus 1 plus 2 raised to n. Show that a n is equal to minus 2 raised to n plus 1 is a solution of this recurrence relation. 5. Find all the solution of the recurrence relation a n is equal to 2 into a n minus 1 plus 2 into n square. I can suggest some books for further reading. 1. Coleman, Busby, Rose, Discrete Mathematical Structures, 3rd edition, Prentice Hall, Upper Saddle River, New Jersey. 2. Kenneth H. Rosen, Discrete Mathematics and its Applications, 6th edition, McGraw-Hill International Edition. 3rd, C. L. Liu, Elements of Discrete Mathematics, 2nd edition, McGraw-Hill International Edition, Computer Science Series, 1986. 4th, Richard Johnson's Bow, Discrete Mathematics, 6th edition, Pearson Prentice Hall, 2005. 5th, V. K. Balakrishnan, Introductory Discrete Mathematics, 1991. Hope you have followed this session. We will continue our discussion with generating function in next chapter. Till then, goodbye.